Okay, for this last video here, we're going to talk about graphing inequalities. What you will find is that in the Pear Deck, I do ask you to both graph it, do your shading, and complete your characteristic chart. Here, because we've already talked so much about our characteristic charts, I'm not going to do that. I'm just going to graph and shade it. But always remember, if you need any extra help, let me know. Okay, so the first thing you want to do anytime you have an equation or an inequality is figure out what it is that you can successfully graph it. This is going to be an absolute value function. Technically, your inequalities can be anything. I'm just going to do 3 random examples. For our absolute value functions, we need to find our vertex first, as we talked about in the previous video. Your vertex here would be at 1, -2, because it went right 1 and down 2. And then you need to either make your chart or count your slope. I'm personally a fan of just counting my slope. My slope here is 1/3. It is positive, so I need to count up. And then over in each direction, 3. So your rise over your run, and that gets me these 2 points. And then I'm going to keep counting it until I run out of space on my graph. When you actually graph inequalities, there's a couple details you got to remember. First off, since it is not equal to, it is just less than. Really, if it's less than or greater than, you are going to have a dashed line. So because this is just less than, I'm going to have a dashed line. If it were a greater than or equal to or a less than or equal to, it would be solid, but I'll get to one of those in a minute. And then you need to look at your actual inequality. This one is less than, which means I need all of the values less than or below this line, which means it is everything below my function, and that is what I'm going to shade in. Everything in this blue region is a solution to my inequality, whereas everything not and everything on the line is not a solution. The reason the line is not a solution, again, is because that was what would be equal to, and we only want less than. So this blue region is my set of answers. For this next one, we are again going to start by just figuring out what the function is and going ahead and graphing it. This is a quadratic. I gave it to you in standard form, which means we need to use our equation x equals -b over 2a to find our vertex. Our vertex then will be at -12 over 2 times 2, which is 4, so -3. My vertex always goes in the middle, no matter what kind of function it is. You want that vertex in the middle so you can actually find it. You need to find points around that. And then I'll plug in things to the left and to the right of it. And for this one, especially, my numbers are going to could be big individually, and so I'm going to type these in. 2 times 25, because that's 5 squared, plus 12 times 5, oopsies, times -5, and then plus 19 gives me 9. And from knowing about quadratics, I know that -1 should also be at 9 then. When I plug in -4, it's 2 times 16, because that's what 4 squared is, plus 12 times -4, plus 19, which gives me 3. And again, that means I also know there is a 3 at -2. And then when I plug in -3, 2 times 9, because that's -3 squared, plus 12 times -3, plus 19, gives me 1. So at -3, I am at 1. At -2, I'm at 3, and so at -4. And then I can get pretty close to having these 9s on the graph as well. Once you have that, now we do start thinking about our inequalities. Since it is either less than or equal to or greater than or equal to, I'm going to have a solid line. So when I draw this in, I am not going to have it dashed like the last problems. That's really indicating to you any points on the line do actually solve the inequality correctly because they're equal to. And then I need to think about the actual value of the inequality. This one is greater than, so it needs to be everything above points on my line, which means it's going to be this whole interior section. So think about finding points on the line that are above it. I draw the arrows to help me out, and then shade that in. So it's everything in that green section and on the line of the parabola. I'm going to go ahead and do one more just to give you another example. This is a radical function, and so it's either a square root or a cube root. This one in particular is a square root. So this is where we're going to use our perfect squares to help us graph it more easily and find some nice numbers. With our square roots, we want to make under the radical equal 0, 1, 4, or 9, so that it's nice numbers that we are allowed to plug in. To make it 0, that would be -3. To make it 1, you're really doing x plus 3 equals 1, that would be -2. To make it 4, you're doing x plus 3 equals 4, which is 1. And to make it 9, it's x plus 3 equals 9. We're going to plug in 6. Actually evaluating these numbers in this function, -3 plus 3 is 0, so that's squared is 0, times 4, which is 0, so this is just -2. -2 plus 3, if I'm plugging this in, is 1. Square root of 1 is 1, so this is really 4 minus 2, or 2. Plugging in 1, 1 plus 3 is 4. The square root of 4 is 2, so this is 4 times 2, or 8. Minus 2 is 6. And then when you plug in 6, 6 plus 3 is 9. Square root of 9 is 3. 4 times 3 is 12. Minus 2 gives me 10. So at -3, I'm at -2. At -2, I'm at +2. At 1, I'm up here at 6. And at 6, it's a little off the graph, but again, I can get close to that. I'm up here at 10. Once you have your points, this is again when we think about the whether it's solid or dashed. Because it is equal to, it's going to be solid. So I'm going to fill that all the way in. Again, if that equal to weren't there, it would be dashed. And this is a less than inequality, which means I want things below my line. And again, I just kind of look at it and figure out where below is, which means it's going to be this entire region under my curve, looking about like